Hello and welcome to Unit 5, Lecture C, Electrons Part 2. So we're going to talk more about electrons today. A lot of what we're going to talk about today is not necessarily going to show up on your exam exactly like you see it here, but it's something that if you understand it, it will help you understand the other questions better. So this is kind of an enrichment and expansion on some of the things that we're going to talk about. So I will clearly point out to you the stuff that you need to memorize and clearly point out to you the things that are extra. All right, the first thing you need to know is that for the model of the atom, we use this wave mechanical model or the orbital notation model. And you do need to know that electrons are found in regions called orbitals. So everyone's going to get that right on their final. Everyone's going to get that memorized. You don't have a choice. You have to know that. All right, so orbitals are three-dimensional regions. They're areas or locations that the electrons will most likely be, and they're arranged in different energy levels depending on how much energy they have. So these quantum numbers or principal energy levels, they're the same as Bohr's energy levels, and we give them numbers corresponding to their periods. So again, if we look at the periodic table, period 1 is your first principal energy level, 2 is your second, 3, 4, 5, 6, 7. Okay, so that's how many energy levels they have. When you drew your Bohr models for 8th grade, if you had something in the third period, you had a nucleus and you had 3 rings for your principal energy levels. Some of you were lucky and you got hydrogen and all you had was one circle and a nucleus. The maximum number of electrons that will fit in any of these principal energy levels also increases as the principal energy levels number increases because the circle gets bigger so it can hold more. If you have a small circle, it holds fewer electrons. Remember, all of the electrons are negative, so we can't put them too close together or they would repel each other and actually push each other out of the energy level. So the principal energy level, number 1, has a maximum of 2. 2 holds a maximum of 8. 3 holds a maximum of 18. And the 4th holds a maximum of 32. And you don't need to know any higher than the 4th principal energy level. So definitely memorize these maximum numbers. Now, if you look at your periodic table, you kind of have to memorize it, but you can also just look at your numbers. If you look up to anything on your periodic table, the highest number you will ever find in the first position is 2. So one of the first things that students tell me is, no, but wait, Mrs. Richards, down here, down at 72 and higher. Look, it starts at 18. Do you see this little asterisk in number 72? Down there at the bottom, there's a footnote that says everything from 72 forward has a 2-8 in front of it. So if you look, the highest number you'll ever find in the first spot is 2. In the second spot is 8. In the third spot is 18. And you really have to go looking for the 32s, but you can find them. The rest of them, we haven't necessarily made elements big enough or that are stable enough to look at its electrons to see what would be the maximum number that you could put in those rings. So you don't have a top number for them. 2, 8, 18, 32, those are the ones that you need to know. All right, those principal energy levels are then split into sublevels, and the sublevels are given letters. Now, our periodic table uses this style of notation. You are not responsible for the sublevels. So I'm going to repeat this. You are not responsible for the sublevels. In your white book, it's going to have dashed lines at this part all about the sublevels. There's a reason I'm teaching you sublevels now. We'll get to it when we do bonding, and some of you want to know why molecules are shaped the way they are. It has to do with these sublevels, so I want to explain it to you. Some of you are going to go on in science. You should know what these sublevels are and that they exist. You might also run into electron configurations that are listed this way when you're on the web, and you might want to know what they mean. So if you look, and it says 1s2, this says in the first principal energy level, there's 2 electrons. And they live in sublevel called S. There's a 2s2 and a 2p6. So this says in our second principal energy level, there's 2 electrons in an S sublevel and 6 electrons in p sublevels for a total of 8. And then there's a 3s2 and a 3p6. So in the third principal energy level, calcium has 8. And then there's just this 4s down here, so it says in the fourth principal energy level, there's 2 electrons that live in an s sublevel. So it's basically saying the exact same thing as ours, it's just more detailed. Bohr's model couldn't explain all of the different spectral lines. There wasn't enough variation. There wasn't enough choices for the electrons to jump around to. But now we can have electrons not only get excited, so if that's ground state, and this is excited state, the way that we write it, you might write 2, 8, 7, 3. But with this type of notation, you can have this 3p electron jump to a 4p sublevel. Or maybe the 3s. Maybe this is still 6, and maybe we have a 3s1, and his electron jumped to this p sublevel. So it gave more choices, and it explains those spectral lines better. So the different sublevels have different amounts of energy. The letters are S, P, D, and F, and they vary in size. So the S sublevel is the smallest, and it only has 1 orbital. Each orbital holds a maximum of 2 electrons, so 1 times 2 electrons gives us a total of 2 electrons. The P sublevel has 3 orbitals, so 3 times a maximum of 2 electrons gives us a total of 6 electrons in a P sublevel. The D sublevels, there are 5 orbitals in the D sublevel, 2 electrons per orbital, which means 10 electrons in the D sublevel. And the F sublevel has 7 orbitals, 7 times 2, 14 electrons total in the F sublevel. The number of sublevels equals the principal energy level. So principal energy level 1 has 1 sublevel, and its letter is S, and S only holds 2 electrons, so the first principal energy level can only have 2 electrons. The second principal energy level gets 2 sublevels, an S sublevel and a P sublevel. So S holds 2, P holds 6, a total of 8 electrons. The maximum number of electrons the second principal energy level holds is 8. The third principal energy level would, of course, have 3 sublevels, S, P, and D. So 2 and 6 and 10 gives us a total of 18. And then, of course, fourth has 4 sublevels, S, P, D, and F, which gives us our maximum of 32. So that's where these maximum numbers came from. For any of you who care where these maximum numbers came from, it's because of the number of sublevels, which tells us the number of orbitals, and therefore the total number of electrons you can have. Excited state electron configurations are going to be any configuration where the electrons are not the way that they're listed on your periodic table. So if we take something simple, so for example, we'll take carbon on the table, which is his ground state configuration, our periodic table says 2-4. So examples of possible excited states are going to be anything that don't match 2-4, but they have to have a total of 6 electrons. So maybe 2-3-1 or 1-5. You have to make sure that the first principal energy level never has more than 2, and the second principal energy level never has more than 8, and the third never has more than 18, etc., etc. So maybe 2-3-0-1, and I still have 6 electrons, and everything is still fine. There are lots of ways to make excited state electron configurations. If you have to make your own on a test, I would recommend doing something really simple like this, so that if you just move one from the highest energy level up and make a new energy level, there's no way you're going to put more than the maximum in any of the slots. Obviously, using that other configuration with the sublevels, carbon's electron configuration was 1s2, 2s2, 2p2, which gives us 6. And then, of course, we have other possible excited electron configurations other than the one you just saw there, because we could have 1s1, 2s2, 2p3, and we can have these guys jump around. You could even have 1s2, 2s1, 2p3, and it would still look exactly the same. It would still look like 2-4 in our notation, but if you use the sublevels, you can see that there's more variation. So this is extra. This you should be able to do. This part right here you should be able to do. Pick out the excited. If it's not on the table that way, then it's excited state. It has to have the same number of electrons. This part is extra. The S and P's are extra. You don't have to do that one. All right, one of the reasons that I like to show you these configurations is because it actually relates to the periodic table and why the periodic table is set up the way that it is. So if we look at our periodic table itself, we have these kind of gaps. So hydrogen and helium have this big gap here. We have this open empty space where it's spread out here. We have these 2 rows way down at the bottom. Why on earth did they set up the table that way? Well, if we look at the periodic table, those sublevels that you don't have to know about, those are lined up so that those are the sublevels that are being filled in. That's why helium has a gap in between it and the other noble gases on our periodic table. So here we have the S sublevels filling in. The first 2 elements in any period have the S sublevels filling in. The next 6 elements in any period have their P sublevels filling in. The next 10 elements have their D sublevels filling in. And the next 14 have their Fs. And you're looking at this saying, all right, yeah, right, Mrs. Richards, where do those 14 go? Why are they down there? Well, if we filled in the table correctly, except it would be longer and not as manageable to use, it would look like this. Those 2 F levels, which we pull out like, let me find my cursor, we pull them out like this down here. This is the way our table is filled up with those F sublevels yanked out of here and put down at the bottom, because these are elements that we don't use very often. They're called rare earth metals. They don't show up in very many compounds. Most of them are radioactive. But if you were to really put them in, they would be right here. So as you would go across, you have 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, and you could follow along and see which electrons are being filled in order. I told you there were orbitals. The different orbitals have different shapes. S orbitals are round. P orbitals are shaped like balloons attached to each other. So your electrons only have a sphere in the S orbital. They can move kind of in this weird figure 8 pattern in the P. In the D, they call it a clover leaf. They've got all kinds of different patterns that they could move in. And then the F sublevels are even more complicated than that. So the electron configurations are on your periodic table. We can use them to identify an element because, of course, you can just add up the numbers and say 2 and 8 is 10 and 2 more is 12. And element number 12 on our periodic table is, ta-da, magnesium. So as long as they're giving you the electron configuration for an atom, you can use them to look them up. They will be different for ions. They're always going to fill in from the lowest to the highest. The only time that they don't is when they're in the excited state, and we have to input energy to make that happen. So if we have lithium in the ground state, if they want to know lithium's ground state electron configuration, you look that up, and it's 2-1. So in the excited state, you're just going to move them out of order, keeping the total of 3 electrons. And again, the easiest thing is going to be to do like 2-0-1, or you could do 1-2. That would also work just fine. Carbon in the ground state, 2-4. In the excited state, I would keep it as simple as possible. 2-3-1 would be the simplest way, and this way you know you haven't gone over the total numbers. The only other thing we need to look at are ions. When we make ions, we are adding or removing electrons, and we always add or remove them from what we call the valence energy level. This last number on any electron configuration is called the valence energy level. These are the electrons that are involved in chemical reactions. So these become really, really important. We want to know how many outermost electrons we have. So lithium, the atom, had 3 protons. So he has 3 electrons, and his electron configuration is 2-1 for a total of 3 electrons. Lithium, the ion, still has to have 3 protons, but to make it +1, remember we're going to have 1 fewer electrons because +3 and -2 is going to give us our total charge of +2. Now he only has 2 electrons. We remove the outermost electron. So his new electron configuration is just 2. These are the electron configurations down here at the bottom. Just 2. We removed the outermost one. You can write 2-0 if you want to. He now has 1 less electron. We're always adding or removing from the valence electrons so that they look like noble gases. Like, what do you mean noble gases, Mrs. Richards? Well, let's look at our periodic table. Here's fluorine. He's element number 9. His electron configuration is 2-7. Okay, so element number 9, 2-7. So if he is, find my cursor again, element number 9, he has 9 protons. So when he's a neutral atom, he has 9 electrons. His electron configuration is 2-7. When he becomes a negative ion, then he needs 1 more electron than he does protons because his charge is -1. So he has 10 electrons. We have to add that 10th electron to his valence energy level, and his electron configuration is now 2-8. Go back to your periodic table. Lithium, when he's an ion, has an electron configuration of 2. So find the element on your periodic table that has an electron configuration of 2, and it's helium. Fluorine, when he becomes an ion, becomes 2-8. Find the element whose electron configuration is 2-8. It's neon. They're going to gain or lose electrons so that they look like noble gases. Let's take magnesium, for example. So magnesium, element number 12. Let me erase my scribblings over his electron configuration. Element number 12. He's 2-8-2. When he becomes an ion, he becomes a +2 ion, so he must lose 2 electrons. Move back 2 squares. That's 1 square. And from sodium to neon, that's the other square. He's going to lose 2 electrons. His electron configuration becomes 2-8. 2-8 looks just like neon. If we're looking at sulfur, element number 16, 2-8-6. His most common negative ion is -2. That means he needs to gain 2 electrons. He's going to move 2 squares this way. 2-8-6 plus 2 more electrons is going to be 2-8-8. He's going to look just like argon. They gain or lose electrons until they look like the noble gases. So you can use your periodic table and move back and forth and see which noble gas configuration they're going to have when they are ions. Now, transition metals, which are the guys in the middle of the table, are a little different. We'll talk about them when we talk about the periodic table. They don't gain or lose from just their valence electrons. They also can gain or lose from that D sublevel, which is one of the reasons I mentioned it up there, even though they don't test you on them. That should be all for electrons. We should have covered everything that you're going to need to know for your exam about electrons. And next, we're moving on to nuclear chemistry.